intro and intermediate, then you have the basics, and then what comes after basics, I don't know. All right. Okay. Well, happy Monday, week 6. Hope all of your classes are going well. All right. So today's topic is floating point numbers. So this marks kind of a transition in the theme of our course. So the first half of our course was very heavy on coding and all kinds of stuff, and then the second half, starting today, is going to talk a lot more on like numeric concepts. So the midterm covers like the coding stuff, and then from here on out, it's going to be a lot more kind of numeric concepts, I guess statistical computation, things like that. And so the final exam is going to be very, very different from the midterm exam. Not that that means anything because you haven't seen the midterm yet, but yeah, a bit of a kind of a theme change. We will cover some numeric methods, so things like root finding methods and some numeric optimization. There's a class, Math 151, that covers numeric methods. That's taught by the math department. It certainly goes a lot more in depth than what I will get into in this class. So this class is kind of like, or at least the couple weeks that we do numeric methods, is like a condensed, light version, the essentials version for stats and data science majors who you aren't required to take, I think it's Math 151, numeric methods. But some of you might take Math 151 and you'll be like, oh man, there's a lot of overlap. Yes, that is true. But yeah, you're not getting a full course. All right. But before we even get into numeric methods, we have to talk about numbers, specifically floating point numbers, because this is how our computer handles numeric values. And we often treat floating point numbers as if they were like real numbers, but they're not real numbers, real being like the real number line, okay? So they're not, these aren't real numbers, they are floating point numbers. And so it all comes down to this, the crux of the problem is that a real number, like think of pi, okay? How many digits of pi are there? And it's like infinitely many, right? It keeps, like, as far as we know, it just keeps going forever. And so how, like if you wanted to store all the digits of pi, how much computer space would you need? And the answer is you can't, right? You would need infinite computer storage, okay? And that's, we don't have that, right? We don't have, it's impossible to do such a thing, okay? And so, what we do is we store our numbers using double precision floating point. We use 64 bits of memory to store a number. And so what that means is that we're only able to store an approximation to these numbers, okay? So, hang on, let me get logged in over on ProLearn over here. So I wrote, the set of real numbers have many definitions and constructions. I don't know if any of you are going to take, 131A, real analysis and things like that. You might not, but anyway, we can think of it as all the points along some infinitely long number line, okay? And all the integer points are equally spaced out, but there are infinitely many real numbers. And then between any two distinct real numbers, whether it's the number 0 and 1, there's infinitely many values. You pick 0 and 0.1, there's infinitely many values between them, right? And so that's what we have. These are like rules that you learned, I don't know when you learned these rules. 4th grade, 5th grade, you start learning some of these like very, very basic rules of of math. You learn things like if you take these two numbers and you add them and you switch the order, it doesn't matter, right? And then you also have these associative things where it's like if you do this plus this, or I'm sorry, B plus C and you multiply it by A, it's the same as doing A times B plus A times C and things like this. You start learning some of these things, I don't know, 5th grade, 6th grade, something around there, right? And these, like, we are, this is ingrained to us, okay? Every number on the real number line has a decimal representation. We can represent any value on the real number line, like pi or whatever, with a decimal representation, square root of 2, these irrational numbers, rational numbers. And it's just that you'll have like point something, 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 and it goes on kind of forever, but technically there is some kind of representation. And so, each of these things is a digit multiplied by a power of 10, right? So 5,413.29 is 5 times 10 to the third, 4 times 10 to the second, 1 times 10 to the 1, 3 times 10 to the 0, so on and so forth. And you guys understand how numbers work, okay? Somewhere, I don't know, probably in middle school, you learn scientific notation where you're like, okay, we can represent all of these numbers. We just kind of roll the decimal point, so it's right behind that first digit, okay? And then so now you have something, point, something, something, something times 10 to the whatever, all right? So you have, we have the kind of the mantissa, which is kind of this point, something, something, something. You have multiplied by 10 to the, you have an exponent, order of magnitude, and then we have a sign. This is just kind of, this is like, how do you express this notation is just trying to explain like what scientific notation is all about here. And so these two things, all of these things are all equivalent to each other. So normally we would write 5,413. You could write 541329, 541,321 times 10 to the minus 2. This is weird, but it's not wrong, okay? And normalized scientific notation, which is probably what we would see we're accustomed to, would be something like you have one digit in front of the decimal point, more digits, and then you have like something like this, 10 to the third. And this is very useful for representing kind of these extremely large or extremely small numbers. So like in chemistry, you have Avogadro's number and, things like the Planck constant in physics and things like that, these really big or really small numbers. And we can do that. And I think like, what is it? Number of atoms in the known visible universe is on the order of, I want to say 10 to the 80 or something like that. It's, you get really big numbers just by, you'd think it's like 10 to the like a million, but it's not. It's like 10 to the 80 or something, I think. I don't know. Don't quote me on that. Maybe somebody could look it up and fact check me here. But all right. So we often represent real numbers using decimal representation. So, you'll see 1/2, you'll write 0.5, and probably in your head, these are like interchangeable. I don't think anybody struggles with seeing something like this. And if you see 0.5, you might just call it out as 1/2, right? Other things, even like these irrational numbers, we can still represent decimal. It's just they're infinite decimal representations, but also just like plain old rational numbers, like 1/3 has an infinite decimal representation, right? It's 0.33333, and like we just know those threes go on forever. And so if you try to write something like 1/3 on a piece of paper, you have to stop somewhere. We have this little symbol that you could write over the last 3. You put a little bar over it to kind of indicate that it's going to go on forever. But if you put it into, say, a calculator or into your computer with a finite number of digits where you don't have this kind of like ability to express mathematical concepts. You just get an approximation, okay? And we often ignore a lot of these things and just kind of pretend like everything's okay, but there's actually some really significant and, I don't know, I wrote profound implications of what happens when you do this. And a lot of the properties that we take as granted with the real numbers no longer work, okay? So here, so I wrote, computers are unable to represent real numbers with infinite precision. Computers don't have infinite storage, so they use a fixed number of bits, in our case 64, and this results in a lot of numbers being represented with approximate representation, right? So if you only were able to write a certain number of digits, you could represent some numbers perfectly. Like 1/2, you can write 0.5, no problem, okay? But then with 1/3, you'd have to do it, I think. Now, computers use base 2 rather than base 10, but a lot of the ideas of like what happens when you use base 10 to store things, the same ideas, it's just the numbers will be different, but the same ideas also apply to what happens when you use base 2, okay? The limits of having just finite representation rather than infinite representation, those implications still have the same kind of similar consequences here. Okay, so I have one of these kind of very, very simple basic calculators, and I recorded a video of myself doing a simple operation here. What is 10 divided by 3 times 3, right? And so, and with real numbers, if we do 10 divided by 3 and we multiply it by 3, we get 10. Okay, there's no surprise there. But let's see if, oh, actually, hang on. Let me open a new tab with this. Okay, so this is me. I recorded this video, and you can see that, well, already where it's going, right? So I start off. So here's the number 10. You do divided by 3. You get 3.333. You take that number and you multiply by 3, and you don't get 10 back. You get 9.999. Okay? And we understand like what happened when you did 10 divided by 3. We got an approximate representation of what basically 3 1/3 is. But then when we multiply this by 3, we don't get 10 back. So we get 9.999. Okay, so so that like breaks this kind of fundamental rule in math that we have, right? On the other hand, if you do 10 times 3 divided by 3, so here we would get, in real numbers, we would get 10. But here, like on the calculator, if you do 10 times 3, and then you divide by 3, you get 10 back, okay? So in one case, like, you get 9.999, and in the other case, you get 10. And so now we see like, oh, the order of operations, whether we do 10 times 3 and then divide by 3, or if we do 10 divided by 3 and then multiply by 3, like, the answers are going to be different, okay? And so this, I wrote, this breaks a fundamental property of the real numbers, okay, a combination of kind of associativity and the commutative property, in that, you know, for real numbers, the order in which you do these operations don't matter, but with floating point numbers or finite approximation numbers, they do make a difference. Just a couple more examples. If you do something like, what is the square root of 2, and then you square it, you won't get 2 back, you'll get 1.99998. On the other hand, if you do 2 squared, and then you take the square root of that, you'll get back 2, right? And so these things also kind of break our rules. All right, let me give you your first view quiz answer. The letter D. D as in dog. D as in dog is our first view quiz answer. Okay, so let's try this. So here I have a is 0.1, and you can try this out on your computer. Okay, so do 0.1 is a, and you ask what is a, and you get 0.1. And then, but for b, write 0.3 divided by 3. Okay, and then so you ask what is b, and you get 0.1. And then you can ask the computer, is a equal to b? And the computer will say false. Okay, so you and here I'll do it right now. Which seems it feels a little bit crazy, right? Is 0.1 equal to 0.1? And the computer is basically telling us no. Here's some more examples. Remind me later. All right, so again, I'm going to say a is 0.1. What is a? A is 0.1. Okay, b is going to be 0.3 divided by 3. All right, and what's b? And then I asked, is a equal to b? That's false. Again, what is a? 0.1. What's b? 0.1. A equal to b? That's false. A equal to a is true. B equal to b is true. What's a minus b? Okay, there's actually a tiny difference. It's not 0. Okay. Okay. What about this? A is going to be 0.1 plus 0.2. Whoops. A is 0.1 plus 0.2. So A is 0.3. Okay, I'm going to say B is going to be 0.3. So here's A being 0.3, B being 0.3. Is A equal to B? Also false. Okay. These are just some of the things that go wrong, where it feels like, okay, 10 divided by 3 times 3 should equal 10, but we're getting something that's not quite right. Okay. Just another example, if I say, hey, make a sequence from 0 to 1 by 0.1, and it goes, okay, 0, 0.1, 0.2, 0.3, 0.4, 0.5, and I say, okay, what is the fourth one here, right, which is going to be 0.3, and what about 0.3? Is A here the same as this? Is this 0.3 same as this 0.3? That comes back and says, no, it's not. Okay. So like, what is this, right? What is this thing? Just some of these other things. Again, 4 divided by 5 times 3 times 5 fourths. So 4/5 times 3 times 5 fourths is 3. 4/5 times 3 times 5 fourths is 3. Is A equal to B? They're not equal to each other, right? Like, you can try all of these out. These are like real legitimate cases where it's like, how this is the number 3 and this is the number 3, but like they're not equal to each other. You can kind of see what's happening a little bit if you change something to like options digits equals 20, and you can say, okay, well, what is 0.1? And so 0.1 isn't when it's stored internally isn't actually 0.1. It's 0.1000000. The approximation, the binary approximation for 0.1 is something like this. The binary approximation for 0.2 is something like this. And so when you do 0.1 plus 0.2, you get this 0.3000004. Okay, and when the binary approximation of 0.3, on the other hand, is 0.299999999. Okay, and so 0.1 plus 0.2 gives us this. 0.3 gives us this. And that's why when we say, hey, is the result of 0.1 plus 0.2 equal to 0.3, it comes back as false, because this value is not exactly the same as this value. And these are just kind of, the same problem where we say, hey, is 10 divided by 3 times 3 equal to 10? 10 divided by 3 times 3, what? It ends up being 9.99999. Is that equal to 10? It's not. And we're basically getting the same kind of thing, except it's happening in binary. So here's just a few examples, okay? Like here's 0.3, 0.4 minus 0.1, 0.5 minus 0.2, 0.6 minus 0.3, and 0.7 minus 0.4. And it all comes back as like, okay, these are all 0.3s, but how many of these are distinct values? Okay, how many distinct values should there be? And off the top of my head, I don't think there's really any way for us to really know easily just by, I don't think any of us have like a true, like such a deep understanding of binary that we can say like, okay, well, this is going to result in this and this is going to result in something different. Okay, so real numbers, these should all be exactly equal, but with approximate representations, these end up being different. So we actually have 3 unique representations of 0.3. We have 0.299 with a bunch of 9s. We have 0.3 with a bunch of 0s and then ending in a 4. These end up 0.2999999, but we also have 0.2999999 ending with a 3. So we have kind of 3 unique representations of things that, the real number calculations should have all resulted in the exact same value of 0.3, but we're getting something just a little bit off from each other. So these are just kind of like things that break down when we do floating point numbers. Okay, so we got to talk about binary numbers. So we're accustomed to using decimal representation, probably just because we have 10 fingers, and so we have 10 unique digits, 0 through 9, and we can represent everything, all the numbers. And similarly, we can do binary representation. With binary representation, we have either a 0 or a 1. We have 2 unique digits, and we can also represent all the numbers on the real number line in binary as well. To kind of make sure that we're dealing with binary, we're going to put a little subscript 2 here if it's ambiguous, to say, hey, this is going to be a binary representation. So in binary, you have the ones place. So in decimal, you have the ones place, you move over, you have the tens, and then you move over and you have the hundreds, 10 squared, you move over again, you have the thousands, 10 to the third. In binary, you start off with the ones, 2 to the 0, you move over 1 space, and then you have the twos place, you move over another space, and now you have the 4s, the 2 to squared. And if you move over again, you have the 8s, the 2 to the third. And so this is the first 15 digits, or first 15 numbers in binary, or 16, 0 through 15 in binary, right? So you have 0, 0, 0, 0 for 0, and then for 1, the ones becomes a 1. For 2, you get a 1 in the 2's place, a 0 in the 1's place. 3 is 2 and 1, a 1 in the 2's, a 1 in the 1's. 4 is, you get a 1 in the 4's place, 0, 0. 5 is a 4 plus 1. 6 is 4 plus 2 plus 0. 7 is 4 plus 2 plus 1. Now you have an 8. 8 plus 1. 8 plus 2 is 10. 8 plus 2 plus 1 is 11. 8 plus 4 is 12. 8 plus 4 plus 1 is 13. 8 plus 4 plus 2 is 14. And 8 plus 4 plus 2 plus 1 is 15. And then you would keep going and you'd get 16 and so on and so forth. So this is binary representation. I think most of you have already seen binary before at some point, but if not, each place is just 2 to the 0, 2 to the 1, 2 to the 2, so on and so forth. Okay. Oh, okay, so here's just breaking this down. Here's how we represent the number 11. You have an 8, no 4s, 1, 2, and 1, 1. So 8 plus 2 plus 1 adds up to 11, and this is how we represent the number 11 here. For values that are less than 1, okay, we can represent them in binary as well. It's just things are working the opposite direction. So now that, so in the decimal system, you have your decimal point, and then when you move to the right, the first place is your 10 to the negative 1, the 10th place. 2 spaces to the right of the decimal is 10 to the negative 2, your 100th place, okay? In binary, you have the point, we call that the binary point, one place to the right of the binary point would be the halves place to the -1. Two places to the right of the binary point would be the quarters place to the -2. Three places over would be the eighths place. So in decimal representation, we would have 0.5. In binary, that would be 0.1, okay, because this is representing 1/2. 0.25 in decimal, or 1/4, in binary is 0.01. No halves, 1/4. The value 0.125 in decimal is 1/8. 1/8 in binary is 0.001. No halves, no quarters, 1/8. And so 0.375 is the equivalent to 3/8. 3/8 in binary would be 0.011. We have no halves, but 1/4 and 1/8 would add up to 3/8. So this is how we would get fractional values in binary. And I just kind of want to make sure that makes sense to everybody too. Okay. And so, just like in decimal representation, most of the real numbers have infinite binary representation. So the decimal number 0.1 has the binary representation given by this 0.0001100111, so on and so forth, and it's kind of the 0011 representing going on infinitely. And again, we can't represent this exactly, and so that it kind of gets cut off, and so we're not able to represent the number 0.1 perfectly. And then when you try to do this, you get just some kind of approximate value. And then when you have 0.1 and 0.2, and you ask, is that equal to 0.3? Basically, the binary approximation of 0.1 plus the binary approximation of 0.2 is not equal to the binary approximation of 0.3. And this is kind of the central crux of the problem here. So let's talk about how these numbers all get represented in the computer. We have, so this was a problem, and basically electrical and computer engineers got together and decided upon a standard. And they said, all right, when we make computer chips and these things need to be able to handle numbers, how should we store the numbers? How should this work? And they came up with the IEEE 754 standard for floating point representation. Okay, the standard was revised later in 2008, but we're going to kind of discuss the original specification from 1985. You can read quite a bit about it. There's a very good Wikipedia article on the subject. But this kind of standard came about, and so now pretty much all the computers store numbers in this exact way, right? Because we could have come up with different systems, and that was an issue back in the days, that like different computer systems had different ways to store numbers, and the way you write instructions was different for each computer chip. And so at least on the floating point numbers, I mean, that's still an issue, but where you have like Intel x86 based chips, and you have Apple Silicon M1 based chips, or whatever, it's Apple Silicon M, what is it, what generation it's on now?
I think it is.
Two. You have M1, M2, and I don't know if they have a newer one now, but and then you have ARM, and they all have different kind of instruction sets. There's certain commonalities, but certain things have to be translated from one to another. And that's fine. That's just computer engineering stuff. But at least on the topic of how do we store numbers, that has been decided. And so basically, the way floating point numbers work is they say, all right, we're basically going to do, we store things in binary, and we're going to have it in this kind of normalized, like scientific notation in binary. Okay, scientific notation in binary. So if you think about regular old scientific notation, the first digit isn't supposed to be a 0, right? It should be something between 1 and 9. If you think about normalized scientific notation, it's going to be like 6.02 times 10 to the 23 or something something other than a 0. Well, in binary, because that first digit isn't going to be a 0, it's going to be a 1, okay? If it's not a 0, it's got to be a 1. And so in floating point representation, you're going to have 1 point something 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 times the exponent. In binary, it's going to be 2 to some power. And then you also have a bit for the sign. Is this a positive number or a negative number? Okay. So we have 1 bit for the sign, m bits or digits for the significand, and we also have some bits stored for the exponent. Well, what power of 2 are we multiplying by? Okay. This leading number, the 1 point, isn't stored because we know it's not going to be, we know the digit in front of the point, the binary point, is not going to be a 0, and so we know it's going to be a 1, and so it would be a waste of computer storage to actually store that 1. So we're not going to bother storing that, okay? Okay, so well, let's think about how we would represent some number in binary. So let's say we have this decimal number, 6.375. So basically 6 3/8. How would we store this in binary? Okay, so in binary, I'm going to just kind of convert what's to the left of the decimal point into binary. So 6 becomes 110, right? You have 1 4, 1 2, 0 1s. So 4 plus 2 is 6, okay? And then the points after the decimal in binary, after the binary point, become 0.011, right? And so this is no halves. You have 1/4 and 1/8. So, 2 to the 2, 2 to the 1, 2 to the 0. After the binary point, you have 2 to the -1, 2 to the -2, and 2 to the -3. So you have 1/2, no halves, 1/4, and an 1/8. And so this is how you would represent 6.375 in decimal becomes 110.011 in binary. Okay. And then so if we want to make this binary scientific, we would roll the point 2 places to the left, okay? And so this 110.011 becomes 1.10011. And because we rolled it over 2 spots, we're going to say we have to multiply this by 2 to the 2. Okay? And you could do the conversion and you'll get the exact same value. So so here if I do 1.10011, we have a 1. And then this is 1/2, no quarters, no eighths. This is a 16th, and this is a 32nd. Okay, so again, 2 to the -1, 2 to the -2, 2 to the -3, 2 to the -4, and 2 to the -5. And so that's 1 plus 0.5 plus 0.0625 plus 0.03125. And if you do that, you get 1.59375. And we're multiplying this by 2 to the 2nd power, so multiplying that by 4. And we get back 6.375. So, it feels weird, okay? But these two things are exactly the same, right? It's just like scientific notation, but instead of doing 10 to the some power, it's being multiplied by 2 to the some power. Okay. So that would be kind of this binary floating point. I've given you one answer so far. Okay, let me give you your second answer, which is the letter A. A as an apple. A as an apple. All right, so computers can use different levels of precision to store numbers depending on how much storage it will use. So, your computer, you buy it and it has what? 16 gigabytes of RAM or something like that, probably 8, 32, something around there, okay? It's a lot. But, if you think back to the early days of computer storage, or computers, like how much storage could you have? It was very limited, and so they had to kind of think like, okay, how many bits do we actually need to dedicate to storing a number? And so you had a couple standards come up, and you had single precision floating point, which used 32 bits, and you have double precision floating point, which uses 64 bits. You can also have a long double, but this is not as commonly used, with 80 bits stored for this thing. Okay. In double precision, the way these 64 bits are allocated is you have 1 for the sign, 11 for the exponent, and 52 for the mantissa. So that adds up to 64, and this is how numbers are stored in 64-bit precision on the computer. And this is where we get the name double. So when we talk about the data type that you have in the computer, on R it says type double. It's because it's a double precision floating point. R doesn't support single precision floating point, but if you were, say, working in C or another language, you could create single precision floating point numbers, and that would use less memory as you're doing your computations. Okay, but single precision is kind of like, on this calculator, I have like eight digits in my display. And so there's up to, like, I can store, like, the smallest number I can store would be like 0.000000, like, up to 8 digits and stuff. Okay. And single precision would be like you working only with like 4 or 5 digits, right? So there's less precision that you can store in there. Okay. So this is how our 64 bits are assigned. Again, 1 for the sign, so your bits are labeled 0 through 63. And you got 1 for the sign, 11 for the exponent, and the rest are for your mantissa or the fraction there. Okay. This diagram comes from Wikipedia, so thank you to Wikipedia there. So we have 11 bits stored for the exponent. So we'll keep going. So today's lecture, I'm only going to get through like half of the IEEE 754 specification, and we'll talk about the rest of it on Friday. So you have like a little midterm break in between, but this week we'll just be spent talking about floating point precision. So we're saying we have 11 bits stored for the exponent. Okay, so how many unique values can you represent with 11 bits? You can represent 2 to the 11. Okay, because we got these bits, which are all can either be a 0 or 1. So 2 unique values. We have 11 bits, so we can represent 2 to the 11. 2 to the 11 is 2048. So one number you should all remember is 2 to the 10 is 1024. Okay, so 2 to the 10 is approximately 1,000. It's 1024, and that's a very good number to just kind of keep in mind. That forms a good reference point, because you could say, okay, well, 2 to the 8 is going to be a quarter of that, 256. 2 to the 10 is 1024. So anyway, it's a good one to memorize. So 2 to the 11 is 2048. And so we can represent 2048 different integer exponent values. We reserve 2 of these things for special cases. Okay, all zeros will be a special case. All ones will be a special case. So that leaves us 2046 integers, or 2046 unique values to represent both positive and negative exponents along with 0. And so we're going to say half of those will be positive, 1023. One will be a 0, and then the others will be negative. So we can represent values from exponents as small as negative 1022 to as high as positive 1023. Okay, and so all zeros and a 1 will correspond to negative 1022, and then all 1s and a 0 will correspond to 1023. So to go from 1 down to negative 1022, we say there is a bias of 1023. We're basically taking 1, and if I subtract off 1023, that gives me negative 1022. Okay, and then this value up here is what is it? It's 2046. Okay, and if I do 2046 minus 1023, that gives me 1023. Right. So the stored value of the exponent is off from this. If we turn this into decimal, you take this decimal value and you just subtract off 1023. And so that's the equivalent to doing 2 to the 10 minus 1. So it's basically the number of bits minus 1, 2 to the number of bits minus 1, minus 1. So, if you were to list off all of the possible digits in binary, starting off at 000, that's a special case. 1 becomes negative 1022, 2 becomes negative 1021, so on and so forth, all the way up to this. This is 2046. Becomes 1023, and then all ones has a special meaning here. Okay. So these special exponents, all ones, is used to represent infinity or nan. Okay, and then all zeros is used to represent what we call subnormal or denormalized numbers, which I will explain on Friday, but not today. Okay, just to give us an idea of how this floating point system works, I'm going to have basically a similar system, but using only 8 bits. Okay, so this is not practical, but if we used only 8 bits, and I said we're going to have a very similar system, but we'll have 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa, how would our number system work? Okay, and so this is just like a full a miniature version of the full kind of double precision floating point. Double precision, though, we have 1 bit for the sign, 11 for the exponent, and 52 for the mantissa. But here we're going to just have 1, 3, and 4. But there's still, but I think this will give us a better picture of how the system works. Okay, so the sign bit is simple. If the sign bit is 0, it's a positive number. If the sign bit is 1, it's a negative number. Okay, so just whether that sign bit is either a 0 or 1 determines whether it's a positive or negative number. Now there is one odd quirk, is that now you have 2 representations of 0. You have a positive 0 and a negative 0, because you could have, basically the positive sign and then the negative sign. But we just accept that tiny bit of inefficiency in that we have 2 representations for 0. Okay. All right, let's talk about the 3 bits for the exponent. So the 3 bits for the exponent, with 3 bits, you can have 8 unique values, right? You can go from all zeros to all ones. You have 8 unique values, basically 0 through 7. And so what we need to do is we need to reserve the all 0 case for something special, and we need to reserve the all 1 case for something special as well. So that leaves us with 6 unique values. 6 values, basically going from 1 through 6, and we want half of these to be positive, a 0, and then the rest to be negative. So with that, with 6 unique values, we're going to have represent positive 1, 2, 3, a 0, and a negative 1, and a negative 2. So we can represent exponents as low as negative 2 and as high as positive 3, because with 6 unique values, we want half of them to be positive, a 0, and then the rest to be negative. So we say we have a bias of 3, because going from 6 down to 3, we have to do 6 minus 3. To go from 1 to negative 2, we have to do minus 3. Basically, we're taking the number, the decimal number, and we're subtracting off a 3 to get kind of the corresponding exponent. So, in general, if n bits are used in the exponent bias is going to be 2 to the n minus 1, minus 1. So we have 3 bits in the exponent. So our bias is going to be 2 to the 3 minus 1, 2 to the 2, 4 minus 1, and we have a bias of 3. Okay, and then the 4 bits, we have 4 bits for the mantissa. We can always assume the leading digit before the dot is going to be a 1, and we have the 4 bits. Those are going to fill in our mantissa. So we're going to have 1 point something 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 times 2 to the whatever exponent we have. So let's look at this number. I've got 0, 1, 0, 1, 0, 1, 1, 1 in binary in my miniature floating point system, and I'm going to ask, what is this value in decimal? Okay, or what number does this represent? So first digit is the sign, the next 3 is for the exponent, and the last 4 are the mantissa. Okay, so the sign bit is 0, so whatever it is, it's going to be a positive number. The exponent bits are 1, 0, 1, and the mantissa bits are 0, 1, 1, 1. Okay, so for the exponent, I can kind of go back to this table, all right, and I could say, okay, if my exponent bits are 1, 0, 1, that corresponds to decimal value 5, and with the bias of -3, this corresponds to an exponent value of 2. Okay, exponent bits are 1, 1, 0, 1. So, but we can also kind of figure this out ourselves, right? Exponent bits are 1, 0, 1. 1, 0, 1 in binary is 5. The exponent bias of 3 is 3. So our exponent value is going to be 2. Okay. The mantissa bits are 0, 1, 1, 1. So if we plug that into the mantissa, we get 1 point, and we have the 4 bits. We're going to plug in 0.0111, 1.0111, and we're going to multiply this by 2 to the 2. Our exponent is 2. So this is equivalent to now rolling the binary point over 2 spots to the right. Okay, so so if I do that, oh, okay, well, I guess so if I do that, I would get 101, okay, 0.11, okay, or here in fractional form, I have 1 half, 0 halves, I'm sorry. This is the quarters, 1/4. This is the eighths, 1/8, and this is the 16ths, 1/16, and I'm multiplying by 2 to the 2. When you do that, you get 4. 0 is 0. 1/4 times 4 is 1. 1/2, or 1/8 times 4 is 1/2, and 1/16 times 4 is 1/4. And so this becomes 4 plus 1 plus 1/2 plus 1/4, or 5.75. So this number 0.101, 0.111 is in decimal is 5.75. Okay, or 1.0111 times 2 to the 2 is 5.75 in decimal. Is that okay? All right, how would we represent the number 2.25 in our floating point system? Okay, so in powers of 2, 2.25 is 1, 2, 0 ones, 0 halves, and 1/4. So in binary, 2.25 becomes 1 0 point, so that's the 2, and then the 1/4, the 0.25 is 0.01. How do we turn this into binary? Well, we have to turn this into kind of normalized binary scientific, so we're going to have 1. We shift this over, so the leading digit is a 1, so we got 1.001 times 2 to the, we rolled it over 1 spot, so it's going to be times 2 to the 1. And so now we need to represent this. We're going to have 0 for the sign bit. Okay, our mantissa bits are going to be 0, 0, 1, and then you can throw in a trailing 0. So our mantissa bits are going to be 0, 0, 1, 0. And then for the exponent, we just need to represent a 1. Okay, we have a bias of 3, so we need to represent the number 4. Okay, so if I do 1 plus 3, we're going to get 4 in binary, which is 1, 0, 0. So the number in binary is going to be 0 for the sign, 1, 0, 0 for the exponent, and 0, 0, 1, 0 for the mantissa. And that's what we have there. Okay, we will pause here for now, and we will explore floating point notation, IEEE 754. Let me give you your last view quiz answer, which is the letter E. E as in elephant. E as in elephant is your last view quiz answer. All right, and so we will continue this on Friday. Good luck as you continue studying for your midterm. So we'll see you on Wednesday, and you can expect to see a seating chart being sent out probably tomorrow. Okay, all right, we'll see you then.